Alright, I am back. Had a bit of a long lunch because I had a headache and took a nap. Not gonna lie, I took a nap. Let's go from 2 to 5 then today, which is pretty decent. Pretty decent work session. Alright, so check, mark, save, bam. Okay, so we left off reading about their kind of like example end-to-end memory system and working a problem through that. The problem, everything was in the TLB and the L1 cache, and so it wasn't really a lot of work. We didn't have to do any page faults. We didn't have to do any cache misses. We didn't have to do any write backs or evictions or anything crazy. Everything was pretty straightforward and easy. And we went through a few of those exercises on the lecture as well. So I don't feel like I'll get much value out of doing more of those, even though the one that I did by hand was pretty easy. So we're going to move on to 9.7 case study. So this is the Intel Core i7 Linux memory system. So instead of the toy memory system, we got our own actual memory system we're going to walk through here. So we conclude our discussion of virtual memory mechanisms with a case study of a real system, an Intel Core i7 running Linux. Although the underlying Haswell microarchitecture allows for full 64-bit virtual and physical address spaces. Oh, interesting. Underlying Haswell microarchitecture allows for full... What does that mean? I'm not sure I understand exactly what that means. The current i7 implementations and those for the foreseeable future support a 48-bit. I guess what they're saying is like and I wouldn't even call it part of the microarchitecture, but he's saying microarchitecture. I don't think he would say that without reason. The instruction set architecture allows for 64-bit addressing. The microarchitecture allows for full 64-bit virtual and physical address spaces. But the current Core i7 implementations and those for the foreseeable future support a 48-bit virtual address space and a 52-bit physical address space. What? Oh, because you want to have potentially more memory. Oh, shit, man. I didn't know that. Makes total sense. (52-bit 4 petabyte physical address space, along with a compatibility mode that supports 32-bit 4 gig virtual and physical address spaces. Damn. I need to message my buddy because we were talking about this stuff the other day, and I need to message him about this insight I was unaware of. Alrighty, let's get back to reading. That was an insight for me. Seems kind of silly that I didn't think of that already, but on these huge servers, you're going to have all these dedicated processes running on the servers, even hypervisors. Sometimes there are hypervisors running entire operating systems. And it's like, yeah, you're going to want to allow for them to have, their own address spaces, the individual operating systems running on a hypervisor, their individual processes inside of those inside of those guest VMs, all going to have their own dedicated address spaces. And like, it's amazing that we can do all that. It is quite amazing. But the point being is that you could have, many tens, hundreds of thousands of these individual private address spaces. And they don't really need to consume a huge amount, more than 48 bits of address space per process. But you also don't want them to be swapping out to disk. So you want to be able to have enough physical memory to allow all those processes to operate sufficiently with enough wiggle room to not have to swap out. And in that case, you're going to want to have a shitload of physical memory. Makes total sense. So one other thing I wanted to mention to my buddy here. All right, back to reading. All right, figure 921 gives the highlights of the Core i7 memory system. The processor package chip includes 4 cores, a large L3 cache shared by all of the cores, and a DDR memory controller. So let's take a look at it. We got registers, got the L1 D cache and the I cache, which is 32 kilobytes, 8-way associative, L2 unified cache, 8-way associative with 256 kilobytes, goes out to L3, unified cache, 8 megabytes, 16-way associative, shared by all cores. And then you got MMU, which has a similar D cache and an I cache, and it's TLB. Has 64 entries, 128 entries, 4-way. It has L2 in front of that. And then that thing reaches out directly to the memory controller shared by all cores. And then a quick path interconnect to other cores. Okay. It's kind of like the diagram. I think it's exactly the same diagram we had in the lecture, so nothing new there. What's interesting is the memory controller is on the CPU die. So let's have a little chitty chat with AI here and say, where is the memory controller typically located at? Is it on the CPU die? Let's say for a normal AMD 64, IA 64 system, is it on the CPU die? Off the CPU die, but inside the package, the CPU package, or on the DIMM, individual DIMMs, or on the motherboard, or on the individual DIMMs. I'm guessing it's on CPU die. Yeah. Older systems, memory controllers on the Northbridge chipset on the motherboard. It's changed when AMD introduced on-die memory controllers with AMD Athlon 64, till later followed with Nehalem era CPUs. I don't think I was around for that. Wasn't paying attention when they had those. What's actually on the DIMMs are mostly passive, but they do include DRAM chips. I have a different buddy I need to talk to about this. They work at Micron, and they told me something the other day that I ignored. Okie dokie. Let's continue onward. Learning so much. And this is an old chip too. Okay, so we got our CPU. Let's continue reading the text first. Each core contains a hierarchy of TLBs, a hierarchy of data and instruction caches, and a set of fast point-to-point links based on the quick path technology for communicating directly with other cores and the external I/O bridge. The TLBs are virtually addressed and four-way set associative. The L1, L2, and L3 caches are physically addressed with a block size of 64 bytes. L1 and L2 are 8-way set associative, and L3 is 16-way set associative. The page size can be configured at startup time as either 4 kilobyte or 4 megabytes. Linux uses 4 kilobyte pages. So, summary of Core i7 address translation. For simplicity, the I caches, ITLB and L2 unified TLB are not shown. Wait a minute, did I skip ahead here? No. Figure 922 summarizes the entire Core i7 address translation process from the time the CPU generates a virtual address until a data word arrives from memory. The Core i7 uses 4-level page table hierarchy. Each process has its own private page table hierarchy. When a Linux process is running, the page tables associated with allocated pages are all memory resident. Although the Core i7 architecture allows these page tables to be swapped in and out. The CR3 control register contains the physical address at the beginning of the L1 page table. Let's reread it. When a Linux process is running, each page table associated with the allocated pages are all memory resident. Although the Core i7 architecture allows for these page tables to be swapped in and out, the CR3 control register contains a physical address at the beginning of the L1 page table. The value of CR3 is part of each process context and is restored during each context switch. So you have CR3, which is the base address to the most significant page table, the origin page table. I don't know what you would call it. And then everything else kind of like, you got to walk the tree to find out the actual physical address for your page, or whether it's a page fault. So yeah, you have your base address for your page table. What else do you have? You have your TLB process virtual address space identifier. That's 2 bits of state. You have all of your registers, your general purpose registers, your multimedia ZMM registers. You have your R flags. You have your program counter, obviously. I'm trying to think of let's do a new chat here. On AMD 64, list out all of the bits of CPU state that need to be stored and restored when performing a context switch. Okay, so we got our general purpose registers, which they're including the instruction pointer in that. Yeah, you got to save everything. R flags register, got to save all that. Makes sense. Segment registers. Even though segmentation is mostly unused in 64-bit, this gets into segmentation, which is like a legacy thing. But I guess modern Linux still saves it for some reason. Even though segmentation is mostly unused in 64-bit mode. CS, SS, DS, ES, usually ignored but architectural present. FS and GS, critical FS base and GS base via MSRs. So these are used for thread level storage, yeah, and per CPU data. I've seen these before. So segmentation is still important, even though they're not teaching in this course. And he said that they're not going to get into it because it's a legacy thing. Segmentation is still important for FS and GS, which I've ran into these registers before. All the control registers. So CO3 is an important one for switching address spaces. Flushes TLB unless PCID is. So PCID, what is that? Process control identifier? I need to figure out I need to figure out what that stands for. AMD 64 PCID. It is process context identifiers. Okay. Okay, so we got CR0, control register 0, which is paging, protection, page fault address, sometimes relevant, page table root, which is CR3, which is the most important part, and then CR4 feature enables. So you got general purpose registers, you got your multimedia registers, you got your control registers, you got your R flags, you got your segmentation or segment registers. And then there's these things, extended control registers. Floating point SIMD state. I don't think there's anything here, is there? Because XMM, that's what I was saying. So the floating point registers, this is super legacy. SSE. So you got your multimedia, which was MM. Then you got XMM, which is SSE, which is streaming SIMD extension. And then you have AVX, which is advanced vector instruction extensions, I think. And extension is abbreviated differently in these two, which I always enjoyed. And then you got AVX 512, which is something I have on my CPU, which is all those ZMM registers. And then op mask registers K0 through K7. I've never used those. MXCR register. This block can be hundreds to thousands of bytes. Yeah, I believe that. Debug registers used for breakpoints. I've never seen these before. DR0 to DR3, because normally your debug is implemented as like a trap instruction in a normal flow of execution, a flow of control, I should say. You just execute a trap instruction, a software interrupt, and that will trap into the kernel, and then the kernel will consult its ptrace information to hand off control to another process that's tracing the current process. But I've never heard of DR0 through DR3, DR6, DR7. I've never heard of these debug registers. Model specific registers. Not all MSRs are per thread, but some must be. So this is FS and GS, and kernel GS. These are per kernel, not per process, okay. Rarely changed per process, but architectural part of state. You got a global descriptor table, interrupt descriptor table. So that's going to be where you locate all of the interrupts. So they'll switch out if you're doing some type of like hypervisor thing, probably. Local descriptor table, task register, typically shared across processor and modern kernels, not switched on every context switch. But if you're in a hypervisor, you're going to switch out the kernels. You're going to have to switch out that stuff. Task state segment, indirectly relevant kernel stack pointer, RSP0, interrupt stack table, updated when switching threads, kernel updates, TSS fields, performance miscellaneous state optional, sometimes included depending on kernel features. Oh, all the performance counters. I forgot about those. Hardware performance counters. Shit, there's like a lot of state. Interrupt state, local APIC context. Minimal versus full context. Execution state, memory view. Yep. So I got all this important stuff, which is all the execution state that you typically think of. R flags, general purpose registers, your XMM, AVX registers, SIMD registers, general purpose, all the execution state, instruction pointer, all that stuff. And then outside of that, you have your memory view, which is mainly the CR3 base address. Okay, let's get back to looking at this diagram here. So CPU generates a virtual address. It goes into the TLB, the MMU, and splits it up into the page offset and the page number. The page number gets split into the TLB tag and the TLB index. TLB index is used to select which set in the TLB to look in. The tag is what we look for. If we find it in there, that's a hit, in which case we go and take the VPN and it gets translated into the physical page number. We add that to the VPO to get the physical address and then out to main memory or out to the L1 cache. Otherwise, if it's a miss, then we use the CR0 register as a base. CR3 register as a base, which actually shows that in the diagram. And then we split the VPN up into 4 sections of 9 bits each. The first 9 bits are used to look up an offset into CR3. Then the value located there is used as an offset. It was used as the base address, and then VPN2 is used as an offset into that table, and you repeat until you get to the very end, in which case you have the PPN, and you can then generate physical address. We then go into the L1 cache, and the L1 cache takes the PPO, splits it up into a CO, a CI, and a CT. The CO is the offset, CI is the set index, CT is the tag. We go into here. This one is less associative than the main memory, than the virtual memory. So virtual memory is fully associative. The TLB is partially associative, and the L1 is also partially associative. So that's why we have 6 bits here for our CI. So we use that to select our set. We then use the tag to select our element in that set, and hopefully that is a hit. If it's a hit, then we have the value stored in cache and we just return to the CPU. If not, we then go out to L2, L3, and main memory. Makes sense. Okay. The TLBs are virtually addressed and 4-way set associative. The L1, L2, and L3 caches are physically addressed with block size up of 64 bytes, and L1 and L2 are 8-way set associative, and L3 is 16-way set associative. The page size can't be configured. You already read that. So core i7 address translation. Figure 922 summarizes the entire core i7 address translation process from the time the CPU generates a virtual address until the data word arrives from memory. This core i7 uses a 4-level page table hierarchy. Each process has its own private page table hierarchy. When a Linux process is running, the page table associate with allocated pages are all memory resident. Although the core i7 architecture allows these pages to be swapped in and out, the CR3 control register contains the physical address at the beginning of the L1 page table. The values of CR3 as part of each process context and restored during each context switch. All right, we already read all that. Okay, on to the next page. Figure 923, which is the diagram above, shows a format of an entry in level 1, level 2, or level 3 page table. When P is equal to 1, which is always the case in Linux, the address field contains a 40-bit physical page number that points to the beginning of the appropriate page table. Notice that this imposes a 4 kilobyte alignment requirement on page tables. Let's think about that. Okay. Yes, that makes sense, because it's going to be all zeros for the actual bytes inside the page. Let me look at this. So P is equal to 1. So where's P at? P is equal to 1. So P is child page table present in physical memory 1 or not 0. Format of level 1, level 2, and level 3 page table entries. What about level 0? Is it level, do we start count at 0? No, start at 1. Each entry references a 4 kilobyte child page table. Okay, if it's 0, then it's located on disk. If it's 1, then this information is, the microarchitecture here is specifying exactly what that needs to be. Whereas P0 is saying it's up to the kernel to decide what that is. Okay, so when P is equal to 1, which is always the case with Linux, how is that true? Oh, because you would never have you'd never be pointing to a page table itself on Linux that's not resident in memory. That's what they're saying. We're not swapping the page tables themselves out to disk. I guess that was a design decision made by the kernel developers. Their address field contains a 40-bit, where's address, base address, 40 most significant bits of the physical base address of the child page table. Well, it's 48. No, it's 64. So 40 would be, what, 24? That doesn't make sense. You got XD unused. Page table physical base address is only from 12 to 50. Oh, that's the 40. Okay, so you got 40 bits there. I got you. So we use 40 bits to address the page number. That means that there is 24 bits in the address space, but because we're limiting the address space, the virtual address space, entirely by 48, then we're going to say there's only 8 bits, and 2 to the power 8 is 256. So in this situation, if I'm reading this right, let me go back. PPN. Where's the PPN here? That means PPO is 12 bits, yeah. No, I said 8 bits. 8 bits. It's 12 bits in this architecture, which means there's 52 bits in this address, but there's only 48 bits in the virtual address. So the physical address space is larger than the virtual address space. The 12 bits for the offset are consistent between both, but we gain an extra 4 bits. We get up to 52 from 48. So that means that the physical address space on this architecture is 2 to the power 4, or 2, 4, 8, 16 times the virtual address space for any given process. And if you include the difference between kernel and user space, it's really 32 times large as the process's address space. That's interesting. Okay. So let's go back here. So 40 bits now are the PPN. So that's a physical page number. The address field contains 40 physical page that points to the beginning of the appropriate page table. Notice that this imposes a 4 kilobyte alignment requirement on page tables. Why does it place 4 kilobytes? Oh, because we have 12 bits. And 2 to the power of 12 is 4K. It is 4K. So that's the size of the page. I mean, we could point to an address. Basically what they're saying is, what I was saying before, is that those 40 bits do not represent a physical address. They represent a physical page number, and you need the extra 12 bits to actually get an address into memory, and they're always going to be 0. So that requires it to be 4K bit aligned. Okay, figure 924, which is in the next page, shows a format of an entry level 4 page table. When P is equal to 1, the address field contains a 40-bit PPN that points to the base of some page in physical memory. Again, this imposes a 4 kilobyte alignment requirement on physical pages. Okay, let's look at this diagram before we move on here, because I want to fully understand these diagrams. So this is the 1 through 3. Format a level 1, 2, 3 page table entries. Each entry references a 4 kilobyte page table, child page table. That is interesting that each page table itself is 4 kilobytes. So let's do a little math here. So if we have 4 kilobytes, which is 2 to the power of 12, and we remove 64 bits, or 8 bytes, so we divide by 8, that's going to give us 512 different entries in this table. Which would be 256 times 2, or 2 to the power of 9, which is exactly the width of our VPN 1, VPN 2, and VPN 3, and VPN 4. Interesting. So each page table has 2 to the 9 entries that are each 2 to the 3 size of 2 to the 3. So that 12 bits of 4K space is divided into 3 bits for the actual entry and 9 bits for the array of entries. Okay. P says we already went over that. And then we got RW, which is a single bit, read only or read write access permission for all reachable pages. User or supervisor kernel mode access permission for all reachable pages. Write through or write back cache policy for the child page. I think everything is write back because of the latencies involved with going to disk. Caching disabled or enabled for the child page table. Okay. 5 is a reference bit set by the MMU on reads and writes cleared by software. 6 appears to be unused. 7, PS, page size either 4 kilobytes or 4 megabytes, defined for level 1 PTEs only. Okay. Not sure how that works. G, which is not documented here. And then we got unused. We got our adder. We got some more unused. And we got XD, disable or enable instruction fetches from all pages reachable from this PTE. So that's your execution bit on the end there. Ooh, okay, the PTE has 3 permission bits that control access to the page. The RW bit determines whether the contents of the page are read, write, or read only. The US bit determines whether the page can be accessed in user mode, protects code and data in the operating system kernel from user programs. The XD execute disable bit, which was introduced in 64-bit systems, can be used to disable instruction fetches from individual memory pages. This is an important new feature that allows the operating system kernel to reduce the risk of buffer overflow attacks by restricting execution to the read-only code segment. As the MMU translates each virtual address, it also updates 2 other bits that can be used by the kernel's page fault handler. The MMU sets the A bit, which is known as a reference bit, each time the page is accessed. The kernel can use the reference bit to implement its page replacement algorithm. Okay, that's good to know. The MMU sets the D bit or dirty bit. That would be on the 4th one, right? Yeah, it's not on the 1, 2, 3 levels. But it sets a dirty bit each time the page is written to. Page that has been modified is something called a dirty page. A dirty bit tells the kernel whether or not it must write back the victim page before it copies in a replacement page. The kernel can call a specific kernel mode instruction to clear the reference or dirty bits. Figure 925 shows the Core i7 MMU. Figure 925 shows that Core i7 MMU uses the 4 level of the page table to translate a virtual address to a physical address. All right, before we get onto that, let's fully understand the level 4 page table entries. Each entry references a 4 kilobyte page. So you got P1 and P0, which effectively are the same. We got the RW, the US, the WT, the CD, the A, and then we got D for dirty bit. So 6 was dirty bit, it's just not used in the 1 through 3. That makes sense. 7 is a 0 because 7 was PS or page size, which we can't set here. G is a global page. Don't evict a TLB on task switch, which wasn't documented here, but is documented here. Global page. Don't evict from TLB on task switch. How do you avoid... Interesting. Okay, I'm not going to question it. Base adder, which is 40 bits that we're looking for, and then XD enable disable instruction fetches. Okay, so now we're going on to figure 29 shows how the Core i7 MMU uses the 4 levels of the page tables to translate a virtual address to a physical address. The 32-bit VPN is partitioned into 4 9-bit chunks, each of which is used as an offset into a page table. The CR3 register contains the physical address of the L1 page table. VPN 1 provides an offset into the L1 PTE page table entry, which contains the base address of the L2 page table. VPN 2 provides an offset into L2 PTE and so on. I don't really need to go over this again. I feel like I fully understand this by now. Yeah, because you're gaining 9 bits each time. So a single entry is 2 to the power of 12, so it's 4K, and then you get 9 bits each time. Can I just type a 9? There we go. So that'll give you 2 megs, and then you gain another 9 bits over here, 1 gigabyte, looks about right, yeah. And you gain another 9 bits over here, which is 512 gigabytes. And then finally you get another 9 bits over here. And that's the total addressable space. So it'd be KM gigabytes. Let's see, KM gigabytes. Wait a minute. This is K, this is M, this is G, this is T, and then you lose 1 bit because the difference between kernel and user space. That last bit is for kernel or user space, and it's sign extended. So that would be 47 if we take out all of this, it'd be 47. And if we took off the 1, it'd be 48. Makes sense. I'm just running some numbers to get a feel for these numbers a little bit. Page global directory, page upper directory, page middle directory, page table. That's probably Intel terminology. Physical page address comes out of that, along with the PPO. PPN gives you the physical address. Okay. Core i7 page table translation, PT page table, PTE page table entry, VPN, which is virtual page number, VPO, which is virtual page offset, PPN, which is physical page number, PPO, physical page offset. The Linux names for the 4 levels of the page tables are also shown. Oh, so these are Linux names, which is global, upper, middle, and page table. The virtual memory of the Linux process. So whenever I looked at these type of diagrams in the past, I always imagined that this was like the remaining, what? So 47 bits, and then you have 3 and 12, 15. I imagine this is like the remaining 15 bits up here. But what it is, it's a remaining 1 bit. So you have 47 bits of address space with a 0. And then you turn that to 1, and then you have the 47 bits with the 1, which are above this area. But then anything above that is just like not addressable by the virtual memory system. And I always imagined it was like all the bits, but it's 1 bit. It's just 1 bit. Okay. Linux virtual memory system. A virtual memory system requires close cooperation between the hardware and the kernel. Details vary from version to version, and a complete description is beyond our scope. Nonetheless, our aim in this section is to describe enough of the Linux virtual memory system to give you a sense of how real operating systems organize virtual memory. and how it handles page faults. Linux machines maintains a separate virtual address space for each process of the form shown in figure 926. Actually did want to look over this because this section has different for each process. As process-specific data, structures, page tables, tasks, and memory management structs, kernel stack. And then you have all of the physical memory. It can't be all of the physical memory, because the physical memory could be bigger than the virtual address space, and you only have 47 bits. You have less than that. So this area above here represents 47 bits of address space. So a subset of that would be even less than 47 bits. And you're telling me that's going to address all of physical memory? Nuh-uh. Doesn't work that way, because physical memory can exceed virtual memory. It is weird that they said physical memory here, though. Let me take a little screenshot of this. And I'm going to go to AI, and I'm going to ask it to explain what the dealy-do is here. In this diagram for Intel, we'll say AMD 64 Linux process address space, it claims that the physical memory is located above the user stack, but I am confused because the user space, the process's address space is 47 bits. The 48th would indicate kernel space of another 47 bits. But physical memory can, let's go all the way back here, can get up to 52 bits on chips I am familiar with, where the virtual address space is limited to 48 bits. So my question for you is, how can 52 bits of physical space map inside the kernel virtual address space? Which is effectively 47 bits. Does the kernel only map specific areas of physical addresses? Virtual versus physical widths. Virtual address space VA on a typical 48 bits canonical, 47. So yes, physical is greater than virtual. Core misconception: the diagram makes it look like physical memory lives inside kernel virtual memory. That's not literally true. Instead, the kernel has virtual mappings that refer to physical memory, not a container that must fully fit it. So that kind of breaks from the discussion that he was having during the lecture about how the kernel just addresses physical memory through the virtual memory system. Kernel VA space. That's interesting because if I cat out proc $$ maps, there's this V syscall thing. There's something about V, VA, VS, VDSO, VV. Like, what is it with the V's? What is it? Kilo, mega, giga, tera, peta, exa. So peta is one step up from tera. Okay. So yeah, that's really misleading that physical memory lives inside of the kernel's virtual memory space. But let's move on. So let's go back over here. Linux maintains a separate virtual address space for each process in the form shown in figure 926. We have seen this picture a number of times already with its familiar code data heap, shared library, and stack segments. Now that we understand address translation, we can fill in some more details about the kernel virtual memory that lies above the user stack. The kernel virtual memory contains the code and data structures in the kernel. Some regions of the kernel virtual memory are mapped to physical pages that are shared by all processes. For example, each process shares the kernel's code and global data structures. Interestingly, Linux also maps a set of contiguous virtual pages equal to the size of the total amount of DRAM in the system to the corresponding set of contiguous physical pages. This provides the kernel with a convenient way to access any specific location in physical memory. For example, when it needs to access page tables or to perform memory mapped I/O operations on devices that are mapped to particular physical memory locations. Other regions of kernel virtual memory contain data that differ for each process. Examples include page tables, the stack that the kernel uses when it is executing code in the context of the process, and various data structures that keep track of the current organization of the virtual address space. Aside, optimizing address translation. In our discussion of address translation, we have described a sequential two-step process where the MMU translates the virtual address to a physical address, and then 2 passes the physical address to the L1 cache. However, real hardware implementations use a neat trick that allows this step to be partially overlapped, thus speeding up access to the L1 cache. For example, a virtual address on the Core i7 with 4 kilobyte pages has 12 bits of virtual page offset, and these bits are identical to the 12 bits of PPO in the corresponding physical address. Since the 8-way set associative physically addressed L1 caches have 64 sets and 64 byte cache blocks, each physical address has 6 cache offset bits and 6 index bits. These 12 bits fit exactly in the 12-bit VPO virtual address, which is no accident. When the CPU needs a virtual address translated, it sends the VPN to the MMU and the VDO to the L1. While the MMU is requesting a page table entry from the TLB, the L1 cache is busy using the VPO bits to find the appropriate set and read out the 8 tags and corresponding data words in that set. When the MMU gets the VPN back from the TLB, the cache is ready to try to match the PPN to one of these 8 tags. So it just does some work up front while it waits on the MMU and TLB. Boom 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 da 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 da. All right, Linux virtual memory areas. How much more do we have to go on this case study? Oh, not much. And then we get into memory mapping, which was part of the lecture, which, you know, I'm going to enjoy that section. And then we get into dynamic. So we got 875. So we got less than what? That's going to be 8 pages, roughly, until we get into our next lecture. So if we go over to, where are we at? 3 here. And if we go over to our lecture for, this would be dynamic memory allocation basic concepts, which, you know, I'm probably not going to get much out of this, but this is going to be an hour. So we can fit that into 30 minutes here. So basically I got an hour, and then I'll do 1 lecture. And we should be done for the day, because I got D&D this evening. Okay. Okie dokie. I like this process of like talking through the material, you know, reading, talking through the material, doing the practice problems, chatting with AI to like explore different aspects of the problem that may not even be covered in the text. Kind of just get my mind kind of thinking outside of not just what's being discussed here, thinking beyond what's discussed here. And then going to the lecture to get reinforcement, chatting with friends about the stuff to get social motivation, social reinforcement. I feel like all of these things are just like really great for learning, especially about hard technical concepts too. It's like, I didn't study any of this stuff when I was in college. I haven't used any of this stuff in my professional work. But it's so fundamental to how computers work that, like, I feel like I owe it to my profession to learn this stuff, to become a better engineer. All right. All right, let's continue reading. Linux organizes a virtual memory as a collection of areas, also called segments or program headers in the ELF world. An area is a contiguous chunk of existing allocated virtual memory whose pages are related in some way. For example, a code segment, a data segment, heap, shared library segment, and user stack are all distinct areas. Each existing virtual page is contained in some area. And any virtual page that is not part of some area does not exist. It cannot be referenced by the process. The notion of an area is important because it allows the virtual address space to have gaps. The kernel does not keep track of virtual pages that do not exist, and such pages do not consume any additional resources in memory, on disk, or in the kernel itself. Figure 927 highlights the kernel data structures that keep track of the virtual memory areas in a process. The kernel maintains a distinct task structure, task struct, in the source code for each process in the system. The elements of the task structure either contain or point to all of the information that the kernel needs to run the process, e.g. the PID pointer to the user stack, name of the executable object file, and program counter. Okay. So we got our task struct. It has an field, probably for memory management. That has a PGD in the struct. PGD is probably the program something or other. Let's see if they refer to it in the text here. I don't see it anywhere. Doesn't say here. Sorry, let's go new chat. In Linux, in the struct, what is the PGD field for? Page table hierarchy. So it stands for page global directory. Points to top level page table user translated project. Okay, so that's your important page, global page table, or page global directory. And then you have your memory map, which is a linked list, interestingly. Which has the start and end addresses, the protection, some other flags, which are things like is this shared or private? Is it anonymous? Does it have a file descriptor backing it? That sort of thing. What's the offset into the file descriptor? There's a lot of data in there. What's interesting is it's a linked list. I wouldn't think that that would be the representation used, but why not? One of the entries in the task structure points to an struct that characterizes the current state of the virtual memory. The two fields of interest to us are our PGD, which points to the base of the level 1 table, the page global directory. Okay, well, I could have just continued reading instead of asking AI for that one. And mmap, which points to the list of VM area structs, each of which characterizes an area of the current virtual address space. When the kernel runs this process, it stores PGD in the CR3 control register. For our purposes, the area struct for a particular area contains the following fields. So we got FVM start. That seems like a typo. I think they just wanted to say VM start. VM end, obviously. I mean, all of those are self-explanatory. Linux page fault exception handling. Okay, we're almost done here. No, we gotta get through memory mapping, damn it. Okay, so suppose the MMU triggers a page fault while trying to translate some virtual address A. The exception results in transfer of control to the kernel's page fault handler, which then performs the following steps. Is virtual address A legal? In other words, does A lie within an area defined by some area struct? To answer this question, the fault handler searches the list of area structs comparing A with the VM start and VM end in each area struct. If the instruction is not legal, then a fault handler triggers a segmentation fault which terminates the process. This situation is labeled 1 in figure 928. Because a process can create an arbitrary number of virtual memory areas using the mmap function described in the next section, a sequential search of the list of area structs might be very costly. So in practice, Linux superimposes a tree on the list using some fields that we have not shown and performs a search on this tree. Is the attempted memory access legal? In other words, does the process have permission to read, write, or execute the pages in this area? For example, was the page fault the result of a store instruction trying to write to a read-only page in the code segment? Is the page fault the result of a process running in user mode that is attempting to read a word from kernel virtual memory? If the attempted access is not legal, then the fault handler triggers a protection exception, which terminates the process. This situation is labeled 2 in figure 928. At this point, the kernel knows that the page fault resulted from a legal operation on a legal virtual address. It handles the fault by selecting a victim page, swapping out the victim page. If it's dirty, swapping in the new page. And updating the page table. When the page fault handler returns, the CPU restarts the faulting instruction, which sends A to the MMU again. This time the MMU translates A normally without generating a page fault. Alright, we're into memory mapping, which I have gone over in the Linux program interface, but probably not in the level of detail that they're going to here. So Linux initializes the contents of a virtual memory area by associating it with an object on disk. Nah. Not really. I feel like that statement's wrong. A process known as memory mapping. Areas can be mapped to one of two types of objects: regular files in the Linux file system. An area can be mapped to a contiguous section of a regular disk file, such as an executable object file. The file section is divided into page-sized pieces, with each piece containing the initial contents of a virtual page. Because of demand paging, none of these virtual pages is actually swapped into physical memory until the CPU first touches the page, i.e. issues a virtual address that falls within that page's region of the address space. If the area is larger than the file section, then the area is padded with zeros. Anonymous file. An area can also be mapped into an anonymous file created by the kernel that contains all binary zeros. The first time the CPU touches a virtual page in such an area, the kernel finds an appropriate victim page in physical memory, swaps out the victim page. If it's dirty, overwrites the victim page with binary zeros, and updates the page table to mark the page as resident. Notice that no data are actually transferred between disk and memory. For this reason, pages in areas that are mapped to anonymous files are sometimes called on-demand zero pages. That's the thing. Because he says here, Linux initializes the contents of virtual memory areas by associating it with an object on disk. Well, anonymous file is not an object on disk. So I feel like that is the phrasing that I take objection to, is the on disk. Because only regular files are on disks. Anonymous files are not on disks. In either case, once a virtual page is initialized, it is swapped back and forth between a special swap file maintained by the kernel. Some kernels have swap files disabled. The swap file is also known as a swap space or the swap area. It used to be a partition when I was doing Linux when I was a young lad. An important point to realize is that at any point in time, the swap space bounds the total amount of virtual pages that can be allocated by the currently running process. Shared objects revisited. The idea of memory mapping resulted from a clever insight that if the virtual memory system could be integrated into the conventional file system, then it could provide a simple and efficient way to load programs and data into memory. As you've seen, the process abstraction promises to provide each process with its own private virtual address space that is protected from errant writes or reads by other processes. However, many processes have identical read-only code areas. For example, each process that runs the Linux shell program bash has the same code area. Further, many programs need to access identical copies of read-only runtime library code. For example, every C program, not every C program, requires functions from the standard C library, such as that is not true. It would be extremely wasteful for each process to keep duplicate copies of these commonly used codes in physical memory. Fortunately, memory mapping provides us with a clean mechanism for controlling how objects are shared by multiple processes. An object can be mapped into an area of virtual memory as either a shared object or a private object. If a process maps a shared object into an area of its virtual address space, then any writes that the process makes to that area are visible to any other process that have also mapped the shared object into their virtual memory. Furthermore, the changes are also reflected in the original object on disk. Changes made to an area mapped to a private object, on the other hand, are not visible to other processes, and any writes that the process makes to the area are not reflected back to the object on disk. A virtual memory area to which a shared object is mapped is often called a shared area. Similarly for a private area. Suppose that process 1 maps a shared object into an area of its virtual memory as shown in figure 929a. Now suppose that process 2 maps this same shared object into its address space, not necessarily the same virtual address space as process 1 as shown in figure 929b. Yep, can totally do that. Since each object is a unique file name, the kernel... Wait a minute. What do you mean it has a unique file name? Since each object has a unique file name, not each object in the mapping, okay. The kernel can quickly determine that process A, it has to do it based on inodes. It can't do it based on file names. Because the, you can have hard links and stuff. The kernel can quickly determine that process A has already mapped this object and can point the page table entries to process 2 to the appropriate physical pages. The key point is that only a single copy of the shared object needs to be stored in physical memory, even though the object is mapped into multiple shared areas. For convenience, we have shown the physical pages have been contiguous, but of course this is not true in general. Private objects are mapped into virtual memory using a clever technique known as copy and write. A private object begins its life in exactly the same way as a shared object, with only one copy of the private object stored in physical memory. For example, figure 930a shows a case where two processes have mapped the private object into different areas of the virtual memories but share the same physical copy of the object. For each process that maps a private object, the page table entries for the corresponding private area are flagged as read-only. I do want to ask AI a question here because I don't think it's going to get answered in the book, and that is, when in Linux, when mapping a file into a shared map, if I update the shared map, it will update the file. However, if another process does writes to that file, are those writes visible to my memory map? That's right, all of I/O uses the page cache. Forgot about that. Yeah, because the other process could be on another core with an entirely different L1, and it's doing its writes into L1, and they're not getting written back, and they're certainly not being written through. And so those writes might not be visible to you if you're running on it, if that process is running on a separate core, because they're not hitting main memory. Now, when your process eventually evicts that cache line up into a higher level cache, like L3, then it'll be visible to all the cores, or main memory will be visible to all the cores, assuming they don't have their own caches. And then there's cache coherency that handles visibility of changes between different individual cores. On AMD 64, does the cache coherency protocols update L1 caches between different cores? And we went over these in that parallel computing class. And fuck, man, it was intense. I didn't really understand most of it, to be honest. Oh, okay. I did want to ask it one other question, which is my original question. So back mapping, a map. If I have a private mapping to a file on disk and something updates the bytes on disk, I imagine my private map, if I have a private mapping that I am reading from, eventually see those updates due to cache coherency and page You're thinking same file, same physical page, cache coherence, all see updates. That's true for map shared, but breaks for map private. The key difference map private is copy on write. When you do that, okay, so even though my process didn't perform a write, a copy happens when some other process, which is not cow or private, performs a write. But in my example, My process did not perform a write. You dumbass, you just said the copy and write happened. Okay. I think AI might be a little off there, but I'm not gonna continue to poke at that. Okay, where did we leave off reading here? Okay, so here we go. For each process that maps a private object, the page table entry for the corresponding private areas are flagged as read-only, and the area struct is flagged as private copy on write, so long as neither the process attempts to write to its respective private area. So as neither process attempts to write to its respective private area, they continue to share a single. So long as neither process. What was the two processes? They continue to share a single copy of the object in physical memory. However, as soon as a process attempts to write to some page in a private area, the write triggers a protection fault when the fault handler notices that the protection exception was caused by the process trying to write to a page in a private copy and write area, creates a new copy, and the page in physical memory updates the page table entry to point to the new copy, and then restores write permission to the page as shown in the figure 930B. When the fault handler returns, the CPU re-executes the write, which now proceeds normally on the newly created page. By deferring the copying of the pages in private objects until the last possible moment, copy and write makes the most efficient use of scarce physical memory. The fork function revisited. Now that we understand virtual memory and network mapping, we can get a clear idea of how the fork function creates a new process with its own independent virtual address space. When the fork function is called by the current process, the kernel creates various data structures for the new process and assigns it a unique PID. To create the virtual memory for the new process, it creates exact copies of the current process struct, area struct, and page tables. It flags each page both in both processes read-only and flags each area struct in both processes private copy and write. When the fork returns in the new process now has an exact copy of the virtual memory as it existed when the fork was called. When either of the processes performs any subsequent writes, the copy and write mechanism creates new pages, thus preserving the abstraction of a private address space for each process. The exec VE function revisited. Virtual memory and memory mapping also play key roles in the process of loading programs into memory. Now that we understand these concepts, we can understand how the exec VE function really loads and executes programs. Suppose that the program running in the current process makes the following call. Say, hey, exec VE A out, null null. As you learned in Chapter 8, exec VE function loads and runs the program containing the executable object file a.out within the current process, effectively replacing the current program with the a.out program. Loading and running a.out requires the following steps. 1. Delete existing user data. Delete the existing area structs in the user portion of the current process virtual address. Map private areas. Create a new area. Struct for the code, data, BSS, and stack areas of the new program. All of these new areas are private copy and write. The code and data areas are mapped to the text and data sections of the a.out file. The BSS areas demand 0, mapped to an anonymous file whose size is contained in a.out. The stack and heap area also demand 0, initially of 0 length. Figure 931 summarizes a different mapping of the private areas. Okay. Map shared areas. If the a.out program was linked with shared objects such as a standard C library libc.so, then these objects are dynamically linked into the program and then mapped into the shared region of the user's virtual address space. Set the program counter. The last thing the exec VE does is set the program counter in the current process context to point to an entry point in the code area. The next time this process is scheduled, it will begin execution from the entry point. Linux will swap in code and data pages as needed. All right, we got about a page and a half left here. User level memory mapping with mmap function. Linux process can use the mmap function to create new areas of virtual memory and to map objects into these areas. The mmap function asks the kernel to create a new virtual memory area, preferably one that starts at address start, and to map a contiguous chunk of the object specified by file descriptor FD to the new area. The contiguous object chunk has a size of length bytes and starts at an offset bytes from the beginning of the file. The start address is merely a hint and is usually specified as null. For our purposes, we will always assume a null start address. Figure 932 depicts the meaning of these arguments. The prot argument contains bits that describe the access protections, I call them protection bits, not permission bits, of the newly mapped virtual memory area, i.e. the VM prot bits in the corresponding area struct. Prot exec pages in this area consist of instructions that may be executed by the CPU. Prot read pages in the area may be read. Prot write pages in the area may be written. Prot none pages in the area cannot be accessed. Let's look at the prototype here. We got mmap. We got a start null, usually nulled. Length, prots, flags, an FD optionally, and an offset optionally. Okay, that makes sense. The flags argument consists of the bits that describe the type of the mapped object. If the map anon flag bit is set, then the backing store is an anonymous object, and the corresponding virtual pages are demand 0. The map private indicates a private copy and write object. The map shared indicates a shared object. For example, buff mmap null size part read map private anon 00. Ask the kernel to create a new read-only private demand 0 area virtual memory containing size bytes. If the call is successful, then buff p contains the address of the new area. The vunmap function deletes regions of virtual memory. The mmap function deletes the area starting at virtual address start and consisting of the next length bytes. Subsequent references to the deleted region result in segmentation faults. Problem 9.5. Let's go ahead and problems. So we just completed 9.4 there. Yeah, so let's go down here to 9.5. Okay. Write a C program mmap copy.c that uses mmap to copy a arbitrary size disk file. To standard out, the name of the input file should be passed as a command line argument. Skip. I've done a lot with mmap as part of the Linux programming interface already. Okay. So now we are in 9.9 dynamic memory allocation. He talks about sbreak and free and malloc. But in reality, sbreak is only one way that the heap is implemented. Sometimes it's implemented with mmap. So we have a bunch of virtual memory stuff, or dynamic memory stuff. Quite a lot. And then a bunch of practice problems which use a bunch of code, which should be interesting. And then we get into garbage collection, mark and sweep, garbage collector basics. I didn't realize we were going to get into garbage collectors, to be honest. Yeah, cover cycles, unreachable objects, common memory-related bugs in C program be referencing bad pointers, reading uninitialized memory, allowing stack buffer overflows, assuming that pointers and the objects they point to are the same size. It's like, no, you need a size of a pointer to an int, not a size of an int. And you should use calloc. Making off by one errors, referencing a pointer instead of the object it points to. Understanding pointer arithmetic, misunderstanding pointer arithmetic. Referencing non-existent variables. Referencing data in free heap buckets, introducing memory links, summary, yay. Okay, let's get into that dynamic memory allocation. It's going to be a long topic, so let's go ahead and start the lecture.
All right, good afternoon, everybody. Welcome, good to see you all. And welcome also to our viewers on video. So last week we looked at this virtual memory mechanism and how it provides so many different useful functionalities to the system, along with this sort of abstraction of having this large contiguous array of bytes. Now, once we're given that large array of bytes, now we have to manage it, and we have to have some mechanism to manage and use that resource. Okay, so that's the topic of our lectures this week is storage allocation and how storage allocators work and how you use them to manage the virtual memory in your system. So the basic idea of a dynamic memory allocator is that applications use it to manipulate virtual memory, to allocate and free chunks of virtual memory that you need in your program. And it's this memory is maintained in an area of virtual memory called the heap. Okay? And all languages have some mechanism for acquiring and manipulating this dynamic memory. So in C, it's the malloc package. Languages like Java have the new method. Now the allocator maintains the heap as a contiguous collection of blocks. Where blocks can be allocated or free. Okay, allocated meaning that they're being used by some program application. Free meaning that they're available to be for use by an application. And there's two types of allocators. The kind of allocator that you find in C, such as the malloc package, it's up to the application to both explicitly allocate the memory and explicitly free it when the application is finished with it. Okay, so the system won't free up any memory that you allocate unless you do it explicitly by calling the free function. But there's other languages that support implicit allocators. And in these implicit allocators, the programmer explicitly allocates memory, but then the system takes care of freeing the memory. Okay, so it's that the burden of freeing the memory is shifted from the application program to the system, and it frees this memory implicitly, sort of behind the scenes, using a process called garbage collection. Okay. So languages like Java, ML, Lisp, they all do implicit. They all support implicit allocators. Now today we're going to discuss explicit memory allocators. On Thursday we'll get into implicit allocators and how they work. Now the allocator in C is provided by the standard C library in a set of functions called malloc package. The malloc function is used to allocate memory, and it takes as input a size argument, which is in bytes, okay? And then it returns a pointer to a memory block that contains at least size bytes. And that block is aligned on x86 systems to 8 bytes, on x86 64 systems to 16 bytes. If size is 0, it returns null. And then it returns -1 like most typical system calls. The programmer frees memory by calling the free function. It takes as an argument a pointer that was returned from some prior invocation of malloc, and it returns nothing. And it frees that, given this pointer that was returned by the prior invocation of malloc, it frees the block at that address, and then returns that block to the pool of available memory. Now there's some other functions. calloc is a version of malloc that gives you an initialized block of memory that's initialized to 0. And realloc, you can malloc a block and then call realloc to change the size of that previously allocated block. And then there's a function called sbreak, which is used internally by allocators to grow and shrink the heap. So when an allocator needs more memory, it calls sbreak to get that additional virtual memory. And then that's added to the heap, the portion. That grows the heap, and then it adds it to the memory that the allocator is manipulating. So here's an example of how we would use malloc in a simple program. We have a pointer to an int, p, and we call malloc, and we want to allocate an array of n ints. So this is sort of the standard way you call it. We want n ints, and so we call it with n times the size of int, because remember the argument is in bytes. Malloc returns a pointer. It returns a generic pointer, void star pointer. So we cast it to a pointer to an int to keep the compiler happy, and then assign it to p. We check for a null return value. So I should point out it returns 0 on error. So we check for this null pointer, which is 0, and print an error if it's null. Now once we've got that pointer, now p we can treat it just like an array. So inside the loop, if we want to initialize it, we loop across the elements of the array, initializing each one to some value. Now when we're finished with this chunk of memory that we've allocated, then we free it by calling free the pointer p. Okay, so we're going to look today at how functions like malloc and free are implemented. So we're going to make a few simplifying assumptions. So I'm going to memory is byte addressed. We know that, but for the purposes of this lecture, we're going to assume that it's word addressed. Okay, so we're just going to look at word-sized units. And I'm going to assume that words are 4 bytes. So basically the size of an int. So this isn't true. I need to fix that. So basically, we're going to think of words as 4-byte quantities, sort of integer-sized quantities. And then our blocks are contiguous chunks of those words that can be either allocated or free. So here we have a portion of the heap which consists of a 4-word allocated block followed by a 2-word free block, followed by another 4-word allocated block, followed by a 3-word free block. And we'll indicate these free blocks by white, and we'll indicate allocated blocks with some shade of color. So let's look now how a sequence of allocations and frees would work. And now notice I'm calling malloc with the size in words, not bytes, just to keep these pictures simpler. So in this, first we call malloc and allocate a 4-word block. Then and that gives us a pointer p1. Then we call malloc again to get a 5-word block, so it just takes one of the free words and allocates it. We call malloc again to get a 6-word block. And then we free the block that's pointed at by p2, this purple block. Okay, so now that frees up that block. And then we do another allocation for a 2-word block. And so the allocator looks to see if it can find a free block that has enough room, and it finds this free block here that has 5 free words, and then it allocates the requested block inside of that free block. Now, allocators work under a lot of different constraints. Okay, so it's hard to write an allocator because of all these constraints. Applications can choose any combination of allocated and free blocks, so you can't predict what an application is going to request. And the application is required to free a block when it frees a block to pass a pointer that was returned from a previous invocation of malloc. Okay, so the application has a few constraints, but really the only one that it has is that the fact that when it frees something, it has to be a pointer from a previous invocation of malloc. Now the malloc operates, or allocators like malloc operate under a lot of different constraints. They can't control the size or the number of the allocated blocks because they have no control over what the application is doing. If an application calls malloc has to respond right away. You might be able to do a more efficient version by batching up requests and then responding to all those requests at once, but the allocator can't do it. When it gets called, it has to process the request and then return right away. It has to allocate blocks from free memory, so in general, it can't touch any allocated block. Right? Once it allocates a block, that block belongs to the application, and the malloc package can't touch it. Now this has a number of implications. So this means that the allocator can't move blocks around, like it can't compress blocks. Like an allocator might want to take allocated blocks and smush them all together to create larger free blocks. Okay, but it can't do that. Okay, so once in a language like C, once an allocator gives a block to an application, it can't touch it. Okay, now blocks because blocks are holding data structures like structs or scalar objects, it has to be aligned to the size of the largest object that can occur. Okay, so for 64-bit systems, that's 16-byte alignment. For 32-bit systems, it's 8-byte alignment. Now allocators are really interesting objects because they combine a trade-off of both sort of running time, sort of speed, and space. So it's kind of a space and performance trade-off. You're trying to optimize both. You want it to run as quickly as possible, but you want it to use the virtual memory in the heap as efficiently as possible. Okay, so now we define these sort of speed and efficiency, memory efficiency metrics. We have 2 metrics that we use. One is called throughput. So given some sequence of malloc and free requests, R0 through Rn-1, so just where R is either a malloc or a free, our goal is to maximize throughput and the peak memory utilization. And what makes malloc such a fascinating and interesting study is that these often conflict. Like, it's very easy to make a really fast malloc that has terrible memory utilization. So throughput is just the number of completed requests per unit time. So if we have 5,000 malloc calls and 5,000 free calls in 10 seconds, then our throughput is 1,000 operations per second. So it's just measuring sort of how efficiently our malloc can process these requests from an application. Now, peak memory utilization is a measure sort of how much useful space, sort of how much it measures how efficiently the allocator uses the heap, or how much is wasted on sort of overheads in the data structures that the allocator has to use. Now, allocators are really interesting objects because they combine a trade-off of both sort of running time, sort of speed, and space. So it's kind of a space and performance trade-off. You're trying to optimize both. You want it to run as quickly as possible, but you want it to use the virtual memory in the heap as efficiently as possible. Okay, so now we define these sort of speed and efficiency, memory efficiency metrics. We have two metrics that we use. One is called throughput. So given some sequence of malloc and free requests, R0 through Rn-1, so just where R is either a malloc or a free, our goal is to maximize throughput and the peak memory utilization. And what makes malloc such a fascinating and interesting study is that these often conflict. Like, it's very easy to make a really fast malloc that has terrible memory utilization. So throughput is just the number of completed requests per unit time. So if we have 5,000 malloc calls and 5,000 free calls in 10 seconds, then our throughput is 1,000 operations per second. So it's just measuring sort of how efficiently our malloc can process these requests from an application. Now, peak memory utilization is a measure sort of how much useful space, sort of how much it measures how efficiently the allocator uses the heap, sort of how much is wasted on sort of overheads in the data structures that the allocator has to use in its implementation. So we'll define a payload. When malloc returns a block, when an application makes a call to malloc, it's requesting a certain size block, and that block is called the payload. So if we call malloc with an argument of 10 bytes, we're requesting a block that has a payload that's at least size 10. Okay, and the 10 bytes that we requested are called the payload. Everything else in that block is overhead. Okay? So after we've run a sequence of requests, the aggregate payload is the sum of all the payloads in the currently allocated blocks. Okay, so in a perfect allocator, the aggregate payload would equal the amount of memory, the total size of all the allocated blocks, because there'd be no overhead. It would just be pure. Every block would be pure payload. Now, we're going to assume that the heap is monotonically non-decreasing, so it always gets bigger. Okay, so this is a simplifying assumption. It's not true in a real malloc package. But we'll just assume that the allocator never decreases the size of the heap. It only increases the size of the heap. Okay. So the peak, given those notions of aggregate payload and heap size, the peak memory utilization after k+1 requests is the sum of all the payloads divided by the total size of the heap. So in the best case, each block in the heap consists of pure payload, so the utilization would be 1. Okay, that's the best we can do. But in practice, each block, the allocator is going to have data structures and padding inside of each block that keep it from getting a perfect utilization. Now, one obvious thing is that since blocks have to be aligned to some, if they're 16 byte aligned, then blocks have to start on 16 byte boundaries, and they have to be at least 16 bytes. So if you were to request a payload of 2 bytes, you'd have a lot of wasted bytes, right? That would sort of decrease the utilization. So this is some of this overhead is unavoidable, but your job as someone who implements malloc is to try to keep that as small as possible. So poor memory utilization, this example that we just talked about, is an example of what we call fragmentation. And there's two types of fragmentation. Internal fragmentation occurs if the payload is smaller than the block size. That was just what we were talking about. And this can be caused by either padding in the block or some kind of data structure in the block that the allocator needs. Sometimes, too, you might make a policy decision that if an application requests a small block, you might return a larger block just to keep, so the blocks don't get sort of splintered up into little chunks. You might want to keep blocks at some minimum size. Now, internal fragmentation, given a series of requests, we can just stop and freeze the heap. And it's very easy to sort of compute the amount of internal fragmentation. We can, at any point in time, we can just look at all the previous requests that we've made and look at the size of the payload for each one of those requests. And so we can determine the level. At any point in time, we can determine the level of internal fragmentation just by looking at the previous requests. So there's another form of fragmentation called external fragmentation, which is a little more difficult to deal with. So external fragmentation occurs when there's enough memory in the heap, but there's no single free block that can satisfy a particular request. Okay, so external fragmentation occurs when the application makes a request for a block, but nowhere in the heap is there a free block that's large enough to satisfy that request. So an example of this, suppose here's the previous example we looked at now, where we have, after a series of malloc and free calls, we have 2 free blocks in the heap, one containing 5 words and the other containing 2 words. So the total number of free words in our heap is 7 words. And now we get a request for 6 words. And we have enough free blocks, we have enough free words in the heap, but we can't satisfy that request. And it's because of this phenomenon called external fragmentation. For example, if we'd have somehow allocated, I don't know, in this case, I don't think we could have avoided the external fragmentation. But nonetheless, there's enough memory here. Just the way that our blocks are configured in the heap, we can't satisfy the request. So in this case, the allocator has to go and get more virtual memory. We would have to get more virtual memory and extend the heap out this way to get a large enough free block. So assessing and sort of understanding external fragmentation is difficult Because unlike internal fragmentation, which depended on the previous request, external fragmentation depends on future requests. So if we look back at this point, and we say, is our heap externally fragmented? Well, it depends, right? We can't say. It turns out it is because the next request is for a block of size 6. But if all of the future blocks, or future requests were for blocks of, say small blocks, then we'd be able to satisfy those, and we wouldn't suffer from external fragmentation. Okay, now, when we build an allocator, all kinds of issues come up that I've glossed over with my simple examples. Right? How do we know, if we call free, how does free know how much memory to free up? Right? We don't call free with a block size, we call it with a pointer. So how does free know how big that block is? How do we keep track of all the free blocks? When we have, when we're satisfying an allocation request, we're going to look for a free block that is larger than the requested size. In that case, what do we do with the extra space in the block? Do we just keep it in the block, and suffer some internal fragmentation? Do we split that block into a smaller block? There's a lot of free blocks in the heap. How do we, when the allocator gets an allocation request, how does it pick from among all of those different free blocks? There's many choices. And then when free tries to insert a free block, where in the heap, where does it insert it? Okay, when it's freed? And how do we reinsert a free block? What does that mean? Okay, so today we're going to look at all of these issues, starting with knowing how much to free. So how big are our block sizes? So the standard method is to keep sort of a word size quantity at the beginning of each block that gives the size of that block in some units. I'm showing them here in word size units. Okay, so that if the application mallocs a payload of size, wants to malloc a payload of size 4, then the allocator needs to find a block of size 5, so consisting of 4 payload words, at least 4 payload words, and then a header block, a header word at the beginning that indicates the total size of that block. And then it returns a pointer, P0, in this case, to the beginning of the payload. Okay, so now we know how big each block is. That's pretty simple. But how we keep track of the free blocks, and this is where it gets interesting. The simplest method is to use we call an implicit list of free blocks. And the idea here is to just put a header in the front of every block in the heap, whether allocated or free. Okay. And then we can use that, starting at the beginning of the heap, we can use that size to walk the heap. Okay, so here's a block of size 5, so we can jump. We know that the next block starts at an offset of 5. With the second block, we know that the next block starts at an offset of 4, and so on. Okay, so we call it an implicit free list because there's no real list of free blocks, but we can traverse all of the free blocks in the heap by traversing all of the blocks in the heap and then just ignoring the allocated blocks. Okay, so now another thing we could do is we could actually use some of the words in the block to create a linked list of some kind, either a singly or doubly linked list. And in this case, it's an explicit list of the free blocks, and we can just walk that list. So here we visit the first free block, and then there's a pointer to the next free block, and so on. So this might be a little more efficient because if we want to traverse the free list, in this case, it's going to be ordered the number of blocks in the list. Okay, it's going to be linear in the total number of blocks in the heap, which might be quite large. There could be lots of allocated blocks. In this case, with an explicit list, any traversal will just be linear in the size of the free list. Question? Yeah, the question is, don't we need a free bit? And we do. And that's the next question. Now another method, a more sophisticated method, instead of having one free list, we can have multiple free lists, where each free list contains blocks of a certain size or certain range of sizes. Or we can get really fancy and use some kind of a balanced tree to sort the blocks, to use the tree to sort them by size order. Now today we're going to look at the implicit list, the simplest kind of free list, and this will identify a lot of basic concepts that are used in the more sophisticated free list. Question?
What do you mean by different free lists for different size classes?
Okay, the question is, what do we mean by different free lists for different size classes? So what I mean is that you identify a range of sizes, and you associate that range with each of these individual free lists. Okay, so one free list might hold blocks of size 0 to 8, and another free list might hold blocks of size 9 to 16, and another free list may be 17 to 32. And so you're guaranteed, you now know, when you're traversing a certain list, you know the range of sizes of the blocks in that list. The reason you might want to do that, by the way, is that imagine you had an infinite number of these lists, one for each possible size. Then every time you allocated a block, you get a block of exactly the size you needed. Okay, so there'd be a minimum amount of fragmentation if you had an infinite number of these size classes. Now, of course, we can't have an infinite number, but the more of these size classes we have, the closer we get to that ideal. Okay. All right, so let's look at how we would build implicit free lists. So as you correctly pointed out, for each block, we need both size and the allocation status. Question?
So why can't we just map every size class to the size system?
Why can't we map every size class?
Why can't we have the number of size classes defined by the number of size classes?
Yeah, so why can't we have an infinite number of size classes? I suppose that'd be an interesting strategy to think about. So you can't have an infinite number of size classes, but you could create a new size class for every new size that you get. And that might work, but it just depends on the range of these size classes and the frequency. And one problem you might have is that you would get, maybe if you only get, it depends on the distribution of the sizes that you get. If you're getting an equal number, if your distribution of sizes is fairly uniform, that would probably work pretty well. If you have if you have a lot of requests for different size classes, you'd have a lot of sort of wasted free lists, I think. So it's a good question. It depends on your workload, and that is a really useful strategy for. So if you have really popular size classes in your requests, then you could just make special case free lists to handle those requests, and then let the other free lists sort of handle a wider range. And imagine if you had a free list where all the blocks were the same, it could be a lot more efficient, right? Because you only need like a bit vector, one bit for each potential block to tell you whether it's allocated or free. So it could be very efficient. You wouldn't need to walk any lists or anything. That's a good question, and that's the kind of thing you'll be thinking about when you do your malloc lab. It's there's a huge design space in implementing malloc functions, and we just explored one tiny part of it just now. So with this implicit list, we're going to need both the size of the block and then its allocation status, whether it's allocated or free. Now we could do this in 2 words, right? But that would be wasteful. So the standard trick is to take advantage of the fact that blocks have to be aligned. Okay, so this is actually kind of a pain in the neck to always have to align these blocks, but we can take advantage of it in this case. And the reason is that if a block is aligned to some, say, 8-byte or 16-byte boundary, then the low order bits are always going to be 0. So if it's aligned to an 8-byte boundary, the three low order bits will always be 0, right? 8 is 1, 0, 0, 0. 16, 1 with 4 zeros. 24, 1, 1, 0, 0, 0. Right? So any 8-byte aligned block has to be size 8, and it has to start on address if that's a multiple of 8. Right? So the size of that block will always have 0, the 3 or 4 low order bits set to 0. So we can take advantage of that, and we'll just have one header word, and we'll use the low order bit to store the allocation status. Okay? And we can do that because we know it's always 0. So we use that low order bit to store the allocation status, and then the remaining bits correspond to the size. And then whenever we want to extract the size, we just mask out this allocation status and always set it to 0 because we know that it's 0. So let's look in detail given this form of implicit list, how we might set things up. So in this case, we're going to assume 4-byte words, okay, int-sized words, and we're going to align on 8-byte boundaries. Okay, so remember the payload of our blocks always has to start on an 8-byte boundary. So the way we do that is we create this unused word at the beginning of the heap that's aligned on this 8-byte boundary, and then the first block in the heap starts at an offset of 4 from the beginning of the heap. So we have the header, which is not aligned, and then we have the payload, which follows. In this case, it's a payload of one word, and that begins on this 8-word boundary. And then the next block, and here we're indicating a free block consisting of 8 bytes. And then that's followed by an allocated block, the one here, of 16 bytes, or 4 words. And now the payload is only 2 words, so we have to pad, right, all of our blocks, because we're assuming that they're aligned on 8-byte boundary. All of our blocks have to be a multiple of 8. Okay, so here's a case of internal fragmentation where we have this extra block in order to maintain the alignment requirement. So that ensures that the next block's payload starts at an 8-byte aligned boundary, and so on. And so we can walk this heap by just following these headers, masking out the allocation bits. And then we have this special epilogue block, which is it's a block with a 0-size payload. It's an allocated block of size 0. Okay, and this is a trick. This is a trick you should use too. So this, and we'll see when we look at coalescing why this helps. But this allocated block at the very end eliminates some sort of special cases when we start to coalesce free blocks. And we'll talk about that in just a moment. But you can finish this allocated block of size 0 is also helpful in terminating when you're walking this list. You can check for a allocated block of size 0 to terminate your search. Okay, so given this kind of structure, then how do we find the free block? Okay, there's a number of different ways. The first way, which is called first fit, is to search the free list from the beginning and just look for the first block we can find that satisfies the request. Okay. So we were asking for a block of size 10. We start at the beginning of the heap, and we walk the list. We walk the heap, looking for a free block that's at least size 10. And it needs to be 10 plus the size of our header too. So so that's a simple idea. Now, some people have proposed an alternative called next fit. So the idea here is that instead of starting over each time from the beginning of the heap to find a block that fits, we just pick up where we left off the last time. Okay, so we scan the heap, and we find a block that's big enough to satisfy the request, and then we remember where we left off. And the next time a request comes in, we pick up the search starting where we left off. Now this seems like it would be a good idea, but empirical studies that people have done have shown that this actually results in worse fragmentation. So you can consider it, but it's generally probably not the best thing to do. Now another alternative is to find the block in the heap, a free block in the heap that's the best fit. So in general, look at all the blocks in the heap and find the block that fits the best. Okay, so if we ask for 10 bytes, try to scan the heap for the block that has the closest to 10 bytes in it. Okay, so that's called best fit. And best fit, you can see it might be more. It sounds like it would be a lot more expensive, right? Because you'd have to look, instead of just looking until you find a fit, you'd have to scan all the free blocks and then pick the best one. Okay, but it has a nice property that it improves memory utilization. Okay, so this is a classic example of the space-time trade-off. So it's slower, but it improves our use, the efficiency of the way we use memory. And there's now we mentioned an alternative way to organize the free list using multiple free lists for different size classes. Now going back to that example again, if we had an infinite number of size classes, one for each size, that would implement best fit with a constant time search. We know exactly which free list to get the block from. Okay. The problem, of course, is how much memory such an organization would use. But the interesting thing about using multiple free lists is that the more of these free lists you have, the closer you get to a true best fit. Okay, so you can approach best fit, and then at some point you begin to get diminishing returns. So that's another sort of design decision: is how many of these multiple free lists do you need, and what should be the size ranges associated with them. Okay, now the question. Now once we found a block, so the application has made a call to malloc. The malloc package has looked in the free list, and somehow using some policy, it's identified a free block in which the requested block will fit. Okay, so now what does it do? The malloc package has to allocate it has to sort of take that. So there's a question: how does it could allocate the whole block and return that back to the programmer, or it could choose to split out a portion, just only the portion of block that's needed, and then create a smaller free block. Okay. So for example, if our application has requested a block of size 4, or I'm sorry, if the malloc package is determined that in order to satisfy the application request, it needs a block of size 4, okay, including the header, then it would look and it would try to find a free block of at least size 4. So let's say it chooses this block for some reason, maybe because it was a next fit picked up here. So this free block is actually contains 6 words. So the allocator has to decide whether just to keep this block of size 6 and just return that back to the application, or whether to split that block into 2 blocks, into an allocated block of size 4, which it then returns to the application, followed by a free block of size 2. Okay, now another question is how to free a block. So the application is requested is called free, and it's asked the allocator to free up a particular block. So this is pretty simple. So if we want to free up this block, you just clear the allocated flag. So if we want to free up the block we just created, you just set the allocated bit to 0, and you're done. It's really simple. But the problem now is this creates external fragmentation. So now if we just free that block of size 4, what used to be a block of size 6 now consists of 2 contiguous smaller blocks, one of size 4 and one of size 2. And so now if that's followed by a request for 5 blocks, now we're stuck. Right? But we've got plenty of memory, and it's even worse. In this case, that memory is all contiguous just because we just cleared the free block, we didn't really notice that it was contiguous, and so we ended up with a situation where we have these 2 contiguous free blocks. So this suggests that when we free up blocks, that we somehow need to coalesce any neighboring blocks to keep blocks as big as possible. Right? So we cannot. One of the invariants of any decent allocator is that there are never contiguous free blocks like this. It's always a free block followed by an allocated block. Okay, so the idea is that if we free a particular, so here we have this allocated block, and if we free that block, then we somehow have to check and see if there's any adjacent free blocks, either following, either next in memory or previous in memory. And if there are, we need to, as part of the freeing process, we need to coalesce those 2 blocks into a larger block, the largest possible block possible. Now, it's pretty easy. If we're asked to free this block, this green block, it's pretty easy to check the next block because we have the size, we have this header, so we know that the next block starts at an offset of 4. So we just check, and we know that the header for that block is at an offset of 4. So we just check the allocated status of that next block using the size field in our header. But what about the previous block? What about this block? How do we check that? Well, given all that we talked about now, the only way we could do it would be to start at the beginning of the heap, and now walk the free list until we get to this current block, remembering the previous block. So each time we traverse, we remember the previous block. Okay, but that would be very inefficient, right? That would make free linear in the size of the heap, because we'd have to, in order to check the previous block, we'd have to walk starting at the very beginning and walk the entire heap. So the solution for that was proposed by a famous computer scientist, Don Knuth, in 1973. It's very clever, but very simple. Like all really good ideas, it seems obvious when you see it, but it turns out to be very clever and a very useful technique. And the idea is just to replicate for each block, replicate the header block at the end of the block. Okay, so each block now contains a header and a footer, identical header and footer. And then this creates sort of an implicit backwards link that we can use. So now, given some block that we want to free, we know that the size of that block will just be one word previous in memory. So we can and it's always a fixed offset, right, of 1 word. So given a pointer to the header of this block, we can look 1 word back to see the size and the allocation status of the previous block. Okay, so that allows us to do that in constant time. And so this footer is sometimes called a boundary tag, and Knuth called it a boundary tag, but we'll just, or we can call it a footer to be sort of parallel with the notion of a header. But the key thing is that it's just identical, has the identical size and allocation status. Okay, now so given, yes, question. So the question is, if we want to have a boundary tag, when we allocate a block, do we need to set aside space for it? And the answer is yes. Most of the time, I'll show you one optimization in a bit. Okay, so given this idea of the boundary tag, and given that we have some allocated block that we want to free, this yellow block, yes, question. Yeah, so just to summarize the question, you need to, when you allocate, when you're looking for blocks that fit, you have to include the size of the header and the boundary tag. It would. Then you'd have to insert padding to get a total block size that's a multiple that satisfies your alignment requirement. Sorry? Yeah, I mean it can. Yeah. If you have, the question is, wouldn't I use a lot of memory? And it can. Again, it depends on the request pattern. If the application is requesting lots of small payloads, then it's going to waste a lot of memory. If it's requesting big payloads, not so bad. Okay, so given that we have some block that we want to free, there's 4 cases that we need to consider when coalescing. The case where the next block is allocated and the previous block is allocated. The case where the next block is free and the previous block is allocated. The case where the previous block is free and the next block is allocated. And the case where both the previous and next block are free. Okay, so in case 1, where we have our allocated block that we want to free, surrounded by 2 allocated blocks, we don't do anything, right? Because we only coalesce free memory. So in this case, we just keep the size of the header and footer stays the same, and we just set the allocation status to free. Now, if the next block is free and the previous block is allocated, what we do is we check the boundary tag of the previous block and we see that it's allocated, so there's nothing to do there. We use the size to check the allocation status of the next block. We use n to jump to the header of the next block. We see that its allocation status is free, so these two blocks need to be coalesced. So we do that by just adding the two sizes together to create this larger coalesced block and setting its allocation status to 0. Now, in the case where the previous block is free, again, we check the boundary tag footer when we see that it's free. So in this case, we have to update the size of the header of the old previous block to create this now new larger coalesced block. And we update the header and the boundary tag footer accordingly. And then in the case where both the previous and the next block are free, we create a single block that's the sum of all three of those sizes. Okay, so is that clear to everybody? Now, as you correctly pointed out, that boundary tags can create additional internal fragmentation because they're not part of payload. So by definition, they're overhead. And so you might ask yourself, are there any cases where you don't need a boundary tag? So which blocks need a boundary tag? Could you get away with, does an allocated block need one? Yeah, if you don't need to coalesce, then you don't need that footer. And what kind of blocks don't you coalesce? Allocated blocks. So maybe we don't need those boundary tag footers on allocated blocks, right? Just on free blocks. But then how are we going to determine that the previous block is allocated or free if an allocated block doesn't have a boundary tag footer? Yes. Sorry? Well, yeah, you would give it one when you free it. But somehow when we're doing coalescing, we need to check somehow that previous block, whether it's allocated or free. Okay? But how does it know whether it's a boundary tag or not? Not sure. Oh, that's okay. Okay. Yes. Bingo. You got it. So remember this. Remember because of our alignment, we've got multiple, at least 3 bits, 3 or 4 bits that are always 0. We're only using one of them. So why not use another one to contain the allocation status of the previous block? Okay. So very good. Right, so the idea. So here's the block that we want to free, and here's its header. And we pass the P to it, and we want to free it. And we've got 1 bit. We know that if we have 8 byte alignment, we know that these are all implicitly 0. So this is an allocated block that we want to free, so it has an allocation status of 1. And let's use one of these spare bits to indicate the allocation status of the previous block. Okay, so if the previous block is allocated, then this would be a 1. And when we're checking to see whether we need to coalesce, we just check that second allocated bit, the allocated bit of the previous block. And if it's 1, we don't need to know what its size is. Okay, we don't need to know where that block is because we're not going to coalesce it. Okay? So here we don't need a boundary tag for an allocated block. But now if that block is free, it'll have a boundary tag. So we'll check if that block is free, then the allocation status will indicate free, and then we know we need to coalesce. And we're going to need a boundary tag because we need to know where that block starts. We need to know its size so that we can go back and update this size to include the total coalesced size of those 2 blocks. So is that clear? Yes. Oh, it's just the allocated bit. So 0 means not allocated, 1 means allocated. Oh, why are the bits always 0? Okay. So blocks have to be aligned to 8 byte boundaries. Okay. Well, payloads have to be aligned to 8 byte boundaries. Okay. That means that blocks have to be, the size of blocks has to be a multiple of 8. Because it's the same thing as when we were doing padding alignment in structs. Each block a size has to be a multiple of 8 so that the block that follows it in memory is aligned properly. Okay? So you guarantee, because of the alignment requirement, you guarantee that of 8 or 16, you guarantee that the size of the blocks are always multiples of either 8 or 16. Okay? And so because that size is always a multiple of 8 or 16, you guarantee that either 3 or 4 bits are all zeros. Okay. Any other questions? Okay, let me summarize then some key policies when implementing an allocator. And I mentioned that the design spaces for these things is really large and really interesting. There's a lot of decisions that you have to make about various policies. So the first is a placement policy, where when we're trying to place a free block, when we're trying to place an allocated block somewhere in a free block somewhere in the list, what policy do we use? First fit, next fit, or best fit? And generally, these things they trade off throughput for fragmentation. Right? So the faster versions, if you're willing to deal with lower throughput, like in the case of best fit, then you can get better memory utilization. Okay. Now there are interesting ways to improve the performance of best fit. You might consider something like good fit, which is sort of a mix of first fit and best fit. So maybe you only search the first, a portion of the heap and then identify the best fit. Maybe instead of searching the entire heap, you just search some portion of the heap and then cut off the search. And then within that region that you searched, you pick the best block. So that's something that called good fit. So that kind of approximates best fit. Or you can use these multiple free lists to approximate best fit. And there, the real advantage of using multiple free lists is that it not only improves memory utilization, but it improves performance too, because the individual lists that you're looking for, you know that they contain blocks that are close to what you're asking for. And since you're dividing all the free blocks up amongst multiple free lists, those free lists will be shorter. Okay, so your searches will take less time, and your probability of finding a block that fits goes up because you're segregating these different size classes. Now we also have to decide on some splitting policy. So when we find a free block that's big enough, what do we do with the leftover part of that block? Once we placed our allocated block into that free block, what do we do with the leftovers? Do we just leave the leftover part in the block itself and return that back to the application, avoiding so that sort of keeping larger blocks, or do we go ahead and split it like I showed before, and going ahead and splitting that block and creating the original free block, allocating a portion of it, and then creating a smaller free block? So that's a policy you may want to for small requests for small payloads, you may up to a certain size you may not want to split. So you may decide not to split blocks smaller. You may decide not to create free blocks that are smaller than some threshold, right? And only splitting for requests for larger blocks. And then there's a coalescing policy. Now we've seen freeing is pretty quick now. It's constant time because of the boundary tag splitters. But you may want to try to speed that up even more by deferring the coalescing. So you can do coalescing every time the free is called, like we just looked at, or you could defer coalescing to some later time. Maybe when you're scanning the free list, trying to place an allocated block in response to a malloc call, maybe as you scan that free list, you could go ahead and do the coalescing at that time. Right? So I'm not saying which one is better. It's really hard to argue for deferred coalescing, given the constant time performance of boundary tag-based coalescing, but it is an option. Okay, so here's a summary then of implicit lists. This is the simplest. Well, it's a very simple kind of allocator. It's the cost to allocate is linear in the size of the heap. Okay, worst case. The cost to free is constant time, even with coalescing. Memory usage will depend on the placement policy: first fit, next fit, or best fit. It's not used in practice because of the linear time cost of allocation. Okay, but it can be used in sort of special purpose allocators where you have a small number of size classes maybe, or that you have a very small or fairly small free list. But the ideas of splitting and coalescing that we looked at are general to all allocators. Okay, so the idea of boundary tag-based coalescing is used regardless of the structure of your free list. So implicit lists are useful to study because they introduce some important concepts, but generally they're not that useful. Okay. So next class we'll look at some more sophisticated organizations of free lists, the explicit list and multiple free lists in particular. Okay. All right, so we'll see you then. Good luck on your shell lab due tonight, and we'll see you on Thursday.
Advanced Concepts Dynamic Memory Allocation. This one is an hour and 22. I'm going to take a break for dinner here, and then I'm going to come back to this. Actually, you know what? I have D&D tonight, so I'm just going to call it here. 4:30. Yeah, we got a lot done here. And then I'll just take another break. Let's do a commit here. Okay, CD back over here. So we finished this lecture. There is a recitation on virtual memory that I might want to watch at some point. Actually, let's check that out. If that's short, we might do it now. So virtual memory 50. Yeah, it's not that short. Okay, so we read all the way up to dynamic memory allocation. So we read all this. Memory mapping. We read the case study. Cool. All right, we are getting through this chapter. We have two major sections to go. So the dynamic memory allocation stuff, I'll start the reading on that tomorrow. So that'll be Thursday's streams. It's probably the entire day is going to be in dynamic memory allocation. And then we have a section on garbage collection. And the common memory related bugs in C probably is not going to take me too long. Garbage collection, depending on how deep they get into implementation, might take a little while. But it seems like they're spending a lot of time on memory allocation and not a lot of time on GC, which makes sense because GC is like a very advanced topic that they just probably just wanted to touch on in this chapter. Okay, so my game plan then is tomorrow to do all the dynamic memory allocation stuff, and then by Friday have the rest of this chapter read, and then the rest of the lectures and recitations I will probably conclude Saturday with, and we're going to be skipping the rest of the labs. The Malik one I actually kind of feel like I want to do at some point, but not in this block of study. I think at some point I'm going to implement my own allocations repo, and when I do that I'll come back and pick up this Malik lab just to get some more experience. Cool. So that will put us... Oh, why does this have a dash here? It should be a space. My bad. My bad. So yeah, that should put us concluding this entire project by the end of Saturday. And if I bust open the learn log here, that would be the end of the second week of April. Which would be the 11th here. So I'll go ahead and just mark that as done here. And that gives us an extra 2 weeks to work on the Linux binary analysis book, which is something that probably is not going to take 2 weeks, to be honest. Cool. All right, I'll take a break here then, and I will be back on tomorrow to get this thing committed. So this is git CI, we'll say finish, or progress on chapter 09, finish lecture 19. Yeah, git push all. And then if I go over here, got my commits in for the day. What did I do here? 10 commits on this day. Oh, that was the day I started on the binary analysis book. Okay. Cool. I'll hop off here then, and I'll be on tomorrow morning to continue reading about dynamic memory allocation.